All right, so let's do one like 14D. So this function is very similar to the one in 14D. It's the function 2x squared plus 4x plus 5. And we're looking to find the value of r sub n, the right-hand sum with n equally spaced subintervals. And then we're going to take the limit as n goes to infinity of that expression. And it's going to be over the interval from 1 to 6 in this problem. So very similar to the one given in 14D, just the numbers changed around a little bit. Let's see what happens. We need the width of each interval. And so that's the length of the interval, which is 6 minus 1 is 5, divided by n, the number of subintervals. So 5 over n is our delta x width. The right-hand endpoints, I'll call that C sub I. We start at A, and since we're going to start with I equal 1, the right-hand endpoints will be A plus I times delta x, right? So when I is 1, I get A plus delta x. So that's the first right-hand endpoint. When I is 2, I'll get A plus 2 delta x, which is the second right-hand endpoint, and so on. So if I plug in, remember the value of A is 1. The value of delta x is 5 over n, so I get 1 plus 5i over n. All right, so now we're ready to find r sub n, which is just the area of our rectangles, right? So we're summing from I equal 1 to n. The height of each rectangle is f of ci, so the function, remember this function up here, evaluated at the right-hand endpoints, ci, which are right here, times what? Delta x, the fixed interval or fixed width of each rectangle, which is 5 over n. So I'm going to plug ci, and here's ci, 1 plus 5i. I'm going to plug that in. I'm going to plug that in for x here and here, right, to evaluate that function. So I've got 2 times x, which is 1 plus 5i over n squared, plus 4x plus 5. So there's the f of ci in the brackets here. And then don't forget I actually did this problem and I forgot my 5 over n. But until I got down to here and I realized it, and I'll tell you about how you can realize if you forget something, but that delta x, right? Don't forget that. Okay, so now what we have to do is some simplification. And so this is algebra. There's a level of algebraic intensity here, I guess. You've got to really be good on your algebra rules. So please review those things. So for instance, when I square the quantity 1 plus 5i over n, I just don't square 1 and square 5i over n and add them together. No, you can't distribute an exponent over a sum. So what is a plus b squared? Remember, you have to follow that out, right? That is going to become a plus b times a plus b, and that's going to be a squared. Outer and inner are both ab, so that's 2ab. Last times last is b squared. So be real careful. A lot of people forget, they just think it's a squared plus b squared. All right, so got to remember your rules of algebra, rules of arithmetic, et cetera, et cetera. So if I expand that out, I get 1 squared is 1, a times b is 5i over n times 2 is 10i over n, and then b squared is going to be 25i squared over n squared. So that's expanding that all the way out. Now what I'm going to do is don't forget this 2's in front of it, so I have to distribute that 2 through. So I get 2 times 1 is 2, 2 times 10i is 20i over n, 2 times this is 50i squared over n squared. And then here, don't forget to distribute your 4 through here as well. So 4 times 1 is 4, 4 times 5 is 20i over n, plus the 5, and then don't forget your delta x is still out there. So I combine like terms before I proceed. That's going to help. Don't try and just distribute the 5 over n and then use the linearity rules right away. Let's simplify. So notice you got in the parentheses here before we go any further, 2 plus 4 plus 5. That's 2 plus 9 is 11, right? I get 11. So go ahead and combine like terms. 20i over n plus 20i over n. Look at the common denominator. They both have a common denominator of n. So 20i plus 20i is 40i over n. And then you've got the 50i squared over n squared times the 5 over n. Okay, so now I'm going to go to the next page. By distributing this through now, go ahead and distribute that through. We get here, right? 5 over n times 11 is 55 over n. 5 times 40 is 200i. N times n is n squared. 5 times 50 is 250i squared. N times n squared is n cubed. So I go and distribute that through. So do all that work, expand, combine like terms, get it in, a manageable form. And now let's begin the process using the linearity rules. I'm going to split this up into the sum of 3 things, and then I'm going to pull any constant multiples out. For this first one, I can pull out the 55 over n. Okay, you could actually leave it in there if you want to think about it, because 55 over n is just one constant. And then the 200 over n squared, I pull that out. I have to leave the I. 250 over n cubed, pull that out, have to leave the I squared. Okay, so this is the linearity rules. And now, what do we know about the summation I equal 1 to n of I? Well, remember the rule that if I have the sum of I equal 1 to n of any constant, it's just the constant times n. And the constant in this case is 1. 1 times n is just going to be n, right? Or 55 over n, don't forget that, times the n is just going to be 55. So this whole sum, right, just this first one comes out to be 55. Over here, what do I do? Well, the sum I equal 1 to n of I, right, here's the power sum formulas which you will be given. So I'm just going to replace it. And I'm going to use this second one. You could use this one here, but algebraically, I just prefer the second one myself. It just makes life easier for me. So I'm going to plug that in for I. That's what I've done right here. Okay. And then for the I squared, I'm going to use this formula here. And I'm going to, again, use these 3. N cubed over 3, n squared over 2, n over 6, right? And that's right there. I've just replaced those, right? And now, essentially, I have an expression in terms of n only. I mean, this is r sub n, but you do want to simplify that, I think. And so that's what we're going to do first. 55 over n times n, we already said is 55. Here I distribute through. 200 divided by 2 is 100. N squared divided by n squared is 1, so I get 100 here. 2 goes into 200 100 times. N up top, n squared on the bottom leaves 1n on the bottom. So that's distributing that through. And then same thing here, I distribute this through, and I get 3 in the bottom, 250 divided by 3 rather, n cubed divided by n cubed is gone. So this is 250 divided by 3. And then here 2 goes into 250 125 times. N squared up top, n cubed on the bottom leaves me 1n. And then 256th, if I divide top and bottom by 2, I get 125 thirds. I've got 1n up top, 3 n's on the bottom. That leaves me 2 n's down here. Okay. And there's r sub n. I'd like to go ahead again and just make it compact as much as I can by combining like terms. 55 plus 100 plus 250 thirds is 715 thirds. Okay. And you can do this. You can do this by hand or whatever, but we have TI-83 or 84 calculators are allowed, and so in this calculation I can do this and use my convert to fraction key, right? I don't know if you know, under math button, if you press the math button, you've got this convert to fraction command. So you can use that command, and voila, there it does all the work for you. I mean, it's not I expect everyone to be able to add fractions by finding the common denominator, which is of course just 3 here, but add those up. At any rate, you get 715 thirds for that. Now I'm going to go ahead and add the 100 over n and the 125 over n because they have a common denominator of n. So 100 plus 125 is 225 over n, and then plus this 125 over 3n squared. So that's more compact. There's the r sub n. And you'll probably see that if you're looking at the answers for my problems, you'll see the more simplified result like this. Okay. There it is. Now, what do? Take the limit as n goes to infinity. Here's the fun part, the easy part, right? I'm going to take the limit as n goes to infinity of this expression. And what's going to happen to these 2 terms here? Well, they're going to go to 0 because the top is fixed. N is getting bigger and bigger and bigger, right? 225 divided by a bigger and bigger number as n goes to infinity. That's getting closer and closer to 0. We say the limit is 0. So these terms are diminishing and becoming insignificant, going to 0. And so we're just left with 715 thirds, which is about 238.33. So this is going to be important as we go later on. We're going to see this is the same thing that is basically what we call the definite integral of the function that we started with, which was 2x squared plus 4x plus 5 on the, from 1 to 6, we'll say, right? So we'll be defining something called the definite integral, and it's the same problem. It's the same problem. So you'll get plenty of practice with these problems. Be careful with your algebra. Show all the steps as I have done in your support. So your homework support should look like this, right? Step by step all the way through. Okay. And of course, on the test as well. Hope this helps clarify things, and we'll do some more later.